Hi everyone, good morning. This is a recording of ARIMA model for the log returns of Apple. So in this file, we're going to use these packages: forecast, quant mode, T series, time series, XTS, ggplot2, TSM packages. So uh, I have already loaded them to my computer. Okay, so by way of review, we will be working on the ARIMA model. And the ideal is that when you model using ARIMA, you have to do diagnostics of the model, and the residual should be white noises, which means they do not have, they are stationary. They're individually, the residuals are individually and independently distributed, or II. Another name for this is IID. IID. Coefficients the coefficients should be statistically significant and uncorrelated. Also, the residuals are stationary and invertible. When we say stationary, so that uh, we can assume that the future will be the same as the past. And then invertible, which means we are not introducing long-term correlations. And lastly, there should be a high degree of fit compared to other models. Okay, so if you're going to use this model and you're going to compare it with other models, perhaps ARIMA models also, that model should be the one with the best fit. Okay, so we're going to use Apple stocks, and I'm going to download here Apple from 2007 up to the end of 2021. So we can run this. Okay, so we now have the Apple data, which we were able to download from Yahoo Finance using the quant mode package. Right. So let's change the object aapl to the smaller letters for easier writing. Okay. So I will not do this anymore, but let's take a look at the structure of Apple. And it's an XTS object. Okay, so there are 6 variables: open, high, low, close. Okay, and the class of Apple, this is an XTS or a zoo object. Okay. Now what we're going to need is only the adjusted price, the 6th column. This is our object. The 6th column is adjusted. That's what we're going to use. So we're going to subset the Apple object, getting the 6th column. If you view Apple, it's now only one column, apple.adjusted. And let's replace the column name of Apple with just ADJ, adjusted. And if we check the Apple, the adjusted price, it's now renamed into adjusted. Okay, so let's have a preliminary look at the our data, Apple data. Let's plot it using the plot function from base R. Okay, so we can see here that the Apple prices from 2007 January up to December, last day of December 2021. You can see here that it's not trend stationary, not trend stationary, which means it has a trend. It may be variance stationary because there doesn't seem to have a non-constancy in variance. It seems to be constant in variance, but however, it's not trend stationary. It means it has a trend. Okay, let's take a look at another way to plot it. So using the autoplot function, and then let's plot this. So this will give us another plot of the Apple object. Okay. All right, then Quant Mode also has a visualization tool. This function chart series is coming from Quant Mode. So let's plot that. Right. So you can see that these three plots give us the time series plot of Apple from 2007 to 2021. Okay. Now we're going to model not the prices itself, but the log returns of Apple. Okay, so we're creating this object lret. Okay, and then we're going to get the log of Apple. Okay, and then difference it. Now, why are we doing this? Why this? Is this correct? Is this mathematically correct? So we first get the log. Okay, so which means that flush so this is Apple, the Apple data. Okay, and then we get the log of this. How do we get the returns? These are the prices. How do we get the log returns? So is it the log of this? So let's illustrate that. Control C, Control V. Is it the log? So the log of the price on January 4. And then let's also get the log Control C, Control V. So the log of that is 0.9365. So how do we get the log returns? Is it by getting the ratio of the two? What is the log returns of the series? Okay, so the long formula is get the log of Apple, okay, and then difference. Okay, difference, which means you get the difference of that. So this is January 4. And then I subtract January, the log of January 3. Okay, so this is the log returns. So what we do with the series is we get the log of each and then subtract. Get the log and then subtract. So if we spell out that formula, so we get the log of your aapl, right? Then after getting the log, let's call this O1, object 1. So we're getting the log of apple, Control Enter. All right, so if I check O1, okay, so we now have the log of each of the prices. And then what we do is get the difference. Okay, the difference of O1 and then log is equal to 1. Log is equal to 1 means you're just getting the difference between each period. There. So let's denote this by O2. So it's the difference of your O1. O1 is the log, right? And then if we view O2, all right, so we now have this object, which is, you can see here, this is the difference, 0.02195. Okay, so how do we get the log returns? The log returns is computed by just move this. So you first get the log of each and then get the difference between the successive logs. So it's the same as using this function. So you get the log and then get the difference. All right. And then we call this log lret. And then lret. Okay, so let's run this. So if you take a look at lret, okay, so these are now the log returns. Okay, and then let's remove the NA here, the first row. We can do this lret, then is.na lret. The exclamation point here means exclude. Exclude all the NAs in lret object. Let's run that and try to see our lret there. Okay, so we now have the log returns, and this is what we're going to model. Okay, actually there are, Quant Mode has pretty powerful tools to get the returns, whether it's daily, weekly, monthly, etc. So here we're going to make use of the daily return function from Quant Mode. Here I presented a reference you could look into, but I'm not going to show that anymore. So I'm creating this object log return 1, and here I'm using daily return of our original object apple, and then type is equal to log. The type can be arithmetic for simple returns, okay, or log for logarithmic returns, which is what we're using. So if I run this, so we now have this lret1 And if I click this, okay, so notice that there's also this first element here, which is 0. Okay, it's a 0 because uh, when when we calculated this, it was empty, but quant mode returns a 0 here. So let's just remove that. Okay, did I remove it here? Okay, here. All right. Then here, instead of using daily ret, we can use period return. Okay. So here, Apple, and then the period is daily. You get the same answer. So the period return or the daily return. So this is more generic because you can use this as to be weekly, monthly, yearly. Okay. All right. So I won't run that anymore. Then the log return, okay, which has log return 1, which has this one. This is practically NA because it has no value. Okay, we can remove that. So LRET -1. And if we check LRET 1, there. Oops, sorry. I think I clicked it twice. Have to run this. And then this one. Check LRET 1. Start with there. Starts with January 4th. Okay, so let's try to see let's plot now our log returns. Okay, I'm using here LRET. It's just the same as our LRET 1. Okay, so let's plot LRET, give it a title, log returns of Apple adjusted prices. Okay, so here we can see that getting the returns of the asset, okay, remove the trend. Okay, so this is now stationary or stationary in trend. And yeah, also in variance, although there are some volatility spikes here, but generally this is also stationary in covariance in variance. Okay, so we can of course use the chart series of the quant mode package. Okay, so this is the plot of our object log returns on Apple. And as I said, this is stationary in mean. This is trend stationary. All right, so let's now check let's check statistically for stationarity. Okay, we are familiar with augmented Dickey-Fuller test, ADF test. So let's see. The null hypothesis is that the time series is not stationary. And then, so we reject that null hypothesis. P-value is 0.01. We reject the null hypothesis that the time series is not stationary. Indeed, the time series, the log return is stationary. Okay, there are other types of, there are other packages that create stationary test. One of which is coming from the Urca package, right? Use the unit root that df function. Okay, so here we're using the log return. Type is equal to none, logs is equal to 0. And if you run this, it will also yield a more comprehensive output. Okay, the null hypothesis is the same also. that the time series is not stationary. So here we have this, the p-value is practically 0, which tells us that we reject the null hypothesis that the series contains unit root. When you say unit root, it has a unit root. It means that the time series is not stationary. Okay, and then these are also tests for the 1%, 5%, and 10% level. Okay, so now we look at the correlogram. The correlogram will tell us what are the possible models that we can use for our time series. So here we're using the ACF function and the PACF function. Okay, I'm sorry about this. This should be LRET. LRET, the log returns. Okay, so let's plot this. Okay, we can see here the ACF and the PACF plot. The PACF tells us of the possible p value, which means the log of our ARIMA. Wala isang plot dito na lang. Okay, PACF. We can see here some significant spikes. And then ACF, also some significant spikes. So perhaps telling us that this could be an ARMA process, right? But it's quite difficult to determine here the possible model. In nowadays, we can use the auto.arima function so that we can see the possible model. Here we can use the TSM package to draw to use an autocorrelation function. This is wrong again. I'm sorry about this. It should be LREP. And let's run this. All right. You can see here that there are some significant spikes. Okay. Here also significant spikes. The PACF, as we know, is used to model your AR, and the ACF to model your MA. So in both cases, there are significant spikes, but some are quite far. Okay. Here, I seem to see a significant spike at the first, at the third, at the sixth. Okay, here also. So this tells us that it could be an ARMA process. Good thing we just don't depend on the visual and the autocorrelation function. We can use the function auto.arima now. So for this, we're going to model our time series, our LREP, and see what let's trace is equal to true. It means it will give us all possible models. And then so let's run this first. It will give us several potential models. Okay, so the auto.arima, so initially it used certain approximations to come up with the best model, and it tells us afterwards it will refit the model, and it's suggesting an ARIMA 501 model. So no differencing, no need to difference because our time series is stationary, but it's suggesting a 5 lags of AR and 1 lag of MA with an Akai key equal to negative 1873. So this is the lowest Akai key here. It's different from the 501 here, okay, because this is just an approximation and then R refitted the model. Okay. 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 All right, let me just delete this. Okay, let me print here, print model. Okay. All right, so we can see here the coefficients. AR1, AR2, AR3, AR4, AR5, MA. Okay, and then we can, generally, we can see whether the coefficients are significant or not. So if you multiply the standard error by 2, okay, for example, 0.08 times 2, that's 0.16, and compare it with the absolute value of your coefficient. If it's less than twice the standard error, then we say that this AR1 predictor for our log return is significant. Okay, all those which is less than, whose coefficient is less than twice that of the standard error. So if you multiply this by 2, that's 0.004, and it's less than 0.0437. So AR2 is significant. So here 0.02 times 2, that's 0.04, and it's greater than 0.01. So AR1 is not significant. AR4 also is not significant. AR5 is significant, and ARMA1 is significant. Okay. All right. So we can test that using the LM test. Let's compute for the COEF test of model number 1. So if I run this, okay, so now it shows to us the parameters AR1, AR2, and if they're significant or not. So AR1 is significant, as we observed a while ago, based on the SE standard error. AR2 is also significant. AR4, the dot here indicates that this is significant at the 0.1 level. Okay, and then AR5, MA, and the intercept, they're all significant. So all right, okay, ignore this. Sorry about this. Okay, so our model is ARIMA 501 with non-zero mean, which means that we have an intercept here, and then the significant predictors are AR1, AR2, AR5, and MA. So I'm writing it down here. So the intercept is 0.00, change this, 0685, 00, 0, and then 0.7341 times log return at t minus 1 minus 0.430437, 437, log 2, and then log 5, 0.0653, and then MA 0.698, 698.1. Okay, so that's log 1 of the error term plus your error term. Okay, so this is our model AR1, AR2, AR5. We're not including AR3 and 4 because they're not significant. Okay, then, so this is our proposed model. After we propose the model, then we go to diagnostics. So what do we have to check? We have to check if the residuals are correlated. Okay, second, let's see if the residuals are stationary. Number three, we test for normality. Okay, so those are the three things that we need to check. So let's go first to autocorrelation. Okay, our model one, so these are the elements of model. Okay, so let's retrieve from model one the residuals. Let's create it into an object called res1. So we now have a res1 in our object here, res1. So these are the residuals, okay, the error terms. Okay, so let's take a look at the chart series of residual. Okay, as we can see here, the residuals, okay, although there seems to be some, perhaps this is 20, maybe 2009, 2008, 2009 during the global financial crisis. And maybe this is 2019, 2020, but we can check that. But you can see here instances of volatility clustering. Okay, so there are residuals here that are way above the average, or way away from the 3 standard deviations or 4 standard deviations from the mean. Okay, we can also plot using the GG histogram to see if there's normality in our residuals. Okay, although there are some outliers here at the end. Okay. So aside from plotting, we can check for autocorrelation among the residuals using the box.test function. Okay, so here we create already. We already created this object res1. So it's an res1 contains all the residuals, all the error terms based on our model. All right. Then we use the box.test. The box.test is used to determine if there's autocorrelation among the lag terms. So there are two methods. You have the box Pierce, and then you have the Leung box. They're practically the same. Okay, so let's take a look at this. Box.test, res1, I'm using here log 10, and then fit df, okay, fit degree of freedom. As you notice, we have 1, 2, 3, 4 parameters. 3 AR, okay, 3 AR, 1, 2, 3 AR, and 1 MA, and the other one is an intercept. So if we take a look at the AR and the MA, you have 3 AR and 1 MA. So I'm going to use here fit degree of freedom is equal to 4 here. Okay, combination of AR, the significant ones are AR1, AR2, AR5, and the MA1. So if we add those, so our fit DF is equal to 4, since they are our significant predictors. So if we run this, okay, so we have, based on box Pierce test, the p-value is 0.331. For the box Leung's test, our p-value is also 0.31, practically the same. So what's our conclusion here? We failed to reject the null hypothesis that there is no autocorrelation among the error terms. So it tells us that the residuals have no autocorrelation. So that's okay as far as the residuals is concerned. All right. Then next, by the way, now the box.test function is quite sensitive to lags. So if I use a bigger lag, let's run this. Okay, you can now see that at log is equal to 18, then our p-value is less than 0.05. Therefore, what's our conclusion here? We reject the null hypothesis that our residuals are not autocorrelated. Okay, so you notice that with just the change in the lag, the box that test generates now a different result. Okay, so ang question, anong gagamitin natin? Okay. So sabi ko dito, notice that using log is equal to 18 produces a different result. Okay, which means that sorry, this should be we reject. We reject the null hypothesis of no autocorrelation because the p-value is less than 0.05. Okay. So a while ago, when we used log.10, it was telling us that since the p-value is around 0.3, then we fail to reject the null hypothesis that the residuals are not autocorrelated. Okay, sorry, yeah, no autocorrelation. So you can see here the sensitivity of the box that test based on the lag. For our purposes, we'll use the 10, okay, and there are some articles that suggest that some suggest that we use 10 and others have different suggestions. But our purposes will use the suggestion of Rob Hindman about the number of the number to use as far as the lag is concerned. Okay. All right. Next, check if the residuals is stationary. So we have here. Okay, we can use the TS display, and it will give us a combined plots. Okay, let's see this time series display. We're plotting residual 1, and we have log.max is equal to 24, and the title is ARIMA 501 model residuals. Let's run this. Okay, so you can see here this TS display function already provides for us the plot of the residuals and the PACF and the PACF and the ACF. Okay, so that's a time series display. So once again, there are significant spikes here, which indicate that okay. All right. Okay, so there's another function called check residuals. This is coming from the forecast package. So aside from TS display, which present to us the combined plot of your residuals and your ACF and PACF, another one which provides a combo plot is check residuals. So here, forecast check residuals. Let's run this. Taking some time to run. Okay, so what do you have here? Okay, it's a combination of the Leung box test gives us a p-value of 0.1298, which means that we fail to reject the null hypothesis that our residuals are not correlated, okay, which is good. And then we have this plot. It gives us the plot of the residuals and the ACF, okay, and also the histogram of the residuals with an overlay of the normal distribution. Okay, so this is more comprehensive. The check residuals also gives us the value of the Leung box test plus the plots of the residuals of the ACF and the histogram of the residuals. Although it does not give us the PACF, but we can easily access that, the PACF. Okay, so also in order to check for, okay, so what are we checking here? We're checking if the residuals are stationary. We know that there's a direct test for that. Yeah, this one, ADF test. Okay, so here you have here the null hypothesis that the residuals contain unit root, which means not stationary, and the p-value is 0.01, which means we reject the null hypothesis. Okay, that the residuals object contain a unit root. It does not contain a unit root, therefore it's stationary. All right, so we are able to address stationary. Okay, however, if we take a look at these plots, okay, there are some, okay, we have here some volatility clustering. And if we're interested in this, in determining that, then ARIMA will not be able to help us, because this one, we can only model using a different method called the Garch model. Okay, and then also we can check for normality. We can see here that there seems to be a flat steepness here, but let's check that statistically using the Shapiro test. Okay, let's plot this again. Check residuals. Okay. All right. Then, just to ask the question, can we still model the residuals within our ARIMA process? Let's now try this. Auto.arima, press 1. Let's trace the suggested models. And you can see here that it's an ARIMA 00. Okay. ARIMA 00 with 0 mean. Best model is ARIMA 00. Okay, which means that we can no longer extract a model out of the residuals. Okay, and lastly, you can actually forecast if you want, for example, to forecast the next 10 days, and we can make use of the predict function. Okay, let's run this, and then we can see here we can see here the forecast. Okay, so which is 3776. What does this mean? If we take a look at our object, it's LRET. Let me see. Nrow 3775. So our observations is 3775. And then if we take a look at this, so because we're having it forecasted in the next 10 days, so it starts at 3776. There. So these are the predictions, and these are the standard errors. Okay, so, and you can also make use of this using the forecast function. So let's try this. You can predict the next 10. And let's print that. Okay, so you can see here from 3776 up to 33785 because we asked R to predict the next 10 values. So these are your point forecast. Okay, and these are your lower and your upper limit. And then we can plot this. Although we can't really see it well because our LRET has 3,775 observations, and we're just predicting the next 10 days. You can see it's more of a straight line. Yeah. Okay. So here you can see the blue one, not really seen because you have 3,775 observations. And then here, just the 10 next days. But the values are already here. Okay. Let me flash that again. Here, 3776 to 3785. And this is the point forecast, and this is the 95% confidence interval that the real value lies between these two. Okay, so thank you so much. This ends our discussion on ARIMA model for aapl adjusted logarithms. Thank you.